Hello, friends. Good morning. Welcome back to another session of artificial intelligence. We are at almost tail end of second unit, second half of second unit, wherein we are looking at the rules for writing the sentences which a human can easily understand and converting them into the sentences which machine could understand without any ambiguity. The reason for doing all this circus is our language, whatever language human uses, be it any language, English or any other language, it is highly ambiguous, it's all context dependent, and hence it becomes difficult for expressing our thoughts to a machine, because machine cannot understand our emotions, machine cannot understand the context and all that. So it has to be somewhere context free version of it. So we are working on that. As a first step, we have converted our sentences. Started with a simple type of sentences which are declarative. That means you are going to declare something, and the meaning of that could be either true or false. So there can't be the third option. So that's the easiest way of starting our exercise. Later, all situations cannot be talked in terms of true or false. Therefore, we started working at the updated version, which we called a first order logic or predicate logic, or sometimes called first order predicate logic, first order calculus. So many names are given to that. And in the last few lectures, we have seen the details about the first order logic and all. So it mainly talks about making things generalized. So it deals with two additional symbols. One is used for there exists some x, and for all x. So if you want to say that something is, some sentence is true for every situation, then we talk in terms of this. And when we try to say that this sentence is true for some situations, then we get into this format. And a sentence we break down into two parts, one subject and one predicate. So everything we represent in terms of a predicate followed by subject in the bracket. So we write subject in the bracket, and the rest of the things like Boolean algebra, other things are applicable. Operators like negation operator, and operator, or operator. Here we call it conjunction operator for and, disjunction for or. And then we have inference operator, and then we have uh, bidirectional inference, and so on. The we in the last classes we have seen how to convert sentences into uh, what you say, a format where it can be represented in our first order logic grammar. Now let us see the application of this. One of them most commonly used is to verify whether the situation holds true or not. So we have to make sure that the given situation holds true or not. So in that, most commonly, as we had discussed earlier, that as a lazy person, we would prefer to work with the simplest possible thing. So if it is and, let us check, is it true for when both are true? If it is or, just verify whether it is false for when both are false, or whether when it is implies, then see whether this is false when this is 1 and 0, and so on. In reality, what we try to do, we just try to disprove that this doesn't hold. So just to disprove, what you have to do is when you give 1 1, it should become 0. then this is wrong. Or when you give 0 0, this should become 1, then this doesn't hold. Or when you give 0 1 1 0, then instead of 0 it should be 1, then this whole thing is wrong. So that's what we were working on. So let us look at where this can be used. So most common application is to verify whether the given first order expression is valid or invalid. So here we are given with four situations, 1 2 3 and 4, and it is asked verify whether these are valid expressions or invalid expressions. So if you look at it, so one thing commonly attracts is our implied statement. Everywhere this inference statement is visible. So you look at everywhere inference statement is visible. So that means the simplest option is to disprove. Instead of trying proving that this inference is true, that means you have to look for three chances, that this is false, this is false, then it is true, this is false, this is true, then it is true, this is true, this is true, then it is true. That's what inference talks about. But one thing we know, that this is true, this is false is true, then try to prove that this is true and this is false. So that one statement if you disprove, then this whole thing gets disproved. So that's what the what do you say, make the things simpler. So instead of working with all four options, try to find one single option which can get you through and prove that this is valid or invalid. If it is valid for 1 0 option, then it must be valid for others also. So try to disprove this. So that's one thing. Second thing is we are talking about for there exists something, for all something, and whenever you're talking about that, we are commonly working with sentences which are made up of alphas and betas. So there is some sentence which is represented by alpha, and there is some sentence which is represented by beta. So there is some relation between alpha and beta, and if you know beta, you can prove alpha. If you know alpha, you can prove beta, or something like that. So different versions are given. So when you are talking about different, then what you can do is just this shortcuts we are using is, when you say there exists x alpha f x, it means you are talking about more than one alpha, and for which one of them it may be true. Now, if to simplify this, let us assume that there are two values each time. Let us assume that there are two values each time. So when you talk about alpha, let us say there are two values, alpha 1, alpha 2. And when you talk about beta, you assume that there are two values, beta 1, beta 2. Okay. Now, when you say this, there exists something, then it is equivalent to saying there exists some alpha 1 or there exists some alpha 2. So one of them is true. So one of the two values, alpha 1 or alpha 2, is true. So that's what this is trying to say. And another version, if you say for all x alpha is true, that means there are two possibilities of alpha, it is alpha 1 and alpha 2, and for both of them it is true, then you are saying that it is alpha 1 and alpha 2. Or you can represent this with our conjunction disjunction form, or you can write a or. Anyone which is comfortable to you, you can use it. Then another thing you can talk of is if alpha implies beta, this is equivalent to saying not alpha or beta. So one way of solving this problem is get every inference to its primary version, and then substitute some alpha beta values and see whether this is true or false and continue. So that's the primitive way. But now what we want to do, we want to simplify our activity. Uh, Being a lazy person, I just want to make sure that things are as simple as possible. So let me start with our first problem. It says beta implies there exists some x for which alpha of x is true. If this is true, then there exists some x, for all x, beta implies alpha of x. Now there are two ways of representing. One, this what is say this operator for all or for some there exist is directly attached to a predicate, or it is attached to a sentence via a comma signature. Whenever you say comma, that means this whole thing is one object, and for this object this is true. That means for this whole object you keep on using x1 x2 x3 different situations, whereas when you say this, then this variation is applicable only to alpha, not for this beta. So yes, definitely, as you said, without example we cannot understand. So let me put that as an example. So it says beta implies, so this is for there exists something, therefore we are talking about two alphas, alpha 1 alpha 2, and because there exists it is, then we can say alpha 1 or alpha 2 implies. Now this is saying this whole thing is true for this. So for all x, this whole thing is true because that is separated by a comma here. That means after comma, whatever is there, everything, this thing is applied to all these things. Whereas this is applied only to this thing. In other places also, we have similar situations. So it says that for all x, so x is connected with this. That means we have two possibilities, alpha 1 and alpha 2, and this beta is a fixed one. We are not written beta of x. That means two betas are not there, it is only one beta. So it says beta implies alpha 1, so this is for all, therefore, and beta implies alpha 2. That's what the actual meaning of this symbols is. So it says beta implies alpha 1 or alpha 2. This implies beta implies alpha 1 and beta implies alpha 2. So this whole thing, first time when you use for x equal to 1, that is alpha 1, and this whole thing is second time when x equal to 2, that is alpha 2. So this whole thing is written two times, and because this is for all, it is separated by conjunction. Done. Now there are two options to verify whether this is valid or not. One, to prove that this is true, or to prove that this is not true. So which one is easier? To disprove is easier because you can just check this false on this side and true on this side. You make this true this side and you make this false this side, and just show that this is not true. True on this side, false on this side. If you just check it, is it true or false? If it is true, then done. If it is not true, then this condition fails. Whatever you are talking about, this implies fails. And when this implies this fails, then this whole thing is invalid. So just try to fail it instead of passing it. Try to fail it because that is easier. Okay, so how do you make this false? This is making false means there are two things separated by and or A and B, and you want this to be false. So for A and B to be false, what is required? Either this should be false, or this should be false, or both should be false. Then only A and B will be false. So just A is false, sufficient. This is going to be false. If only B is false, sufficient. This is going to be false. Okay, let me check it. Done. Okay. So what can we do? We can either say this one is false, or you can say this one is false, or you can say both are false. Okay, let's keep it like this. Now, I want the left hand side to be true. So for the left hand side to be true, what do you want? What is the best way to prove that left hand side is that is what is left hand side? Left hand side is another inference, and you want the inference to be true. And what is the easiest way to make inference true? The easiest way to make inference true is just look at this P conditions. If P is false, this is invariably true. Whereas if P is true, then you have to look at Q also. If P is true and Q is true, then only it is true. Otherwise, if P is false, then irrespective of Q, it is true. Therefore, the simpler way of proving that this is true is just to make sure that left side is false. So that way, the simplest way to make this whole thing true is just make the left side true. The right side be anything. Right side be anything. Therefore, the left side will be true. Right side can be anything. Then this whole thing will be true. Okay. Then what? Beta 1. Beta implies alpha 1 and beta implies alpha 2. So what do you want? You want the right hand side to be false. For right hand side to be false, take any one of them false. Okay, let me take this beta implies alpha 1 is false. Beta implies alpha 1 is false means what? What do you get? Beta implies alpha 1 is false. So if you want this to be false, you can simply assume that beta is false. Yeah, we have assumed beta to be false, and it can be anything alpha. Anything can be alpha. So if I assume alpha to be true, alpha 2 to be true, alpha 2 to be true, then what is happening? Beta is true, alpha is true, so this is true, beta is true, and this is what you want. You want this to be false. So when do you think this will be false? When this is true, this is false, you will get a false. Okay, beta as it is, we wanted this thing to be true, so we set beta equal to true, and that beta has come here as true, and we want the right hand side to be false. So to make right hand side false, one of them, if it is false, that is sufficient. False, beta is true, therefore assume alpha 1 is false. So if alpha 1 is false, beta implies alpha 1. This whole thing becomes false. If this thing becomes false, doesn't make sense whether this is true or false. This whole thing is going to be false. So what has happened? Now we have selected beta as true to make sure that the left hand side is true, and to make sure that the left hand side is true, the right hand side is false. We want one of the brackets to be false, and to make this false, one of them should be false because there is conjunction between them. And let's assume that this is false. So if this is to be false, then this should be true, this should be false. So this should be true, this should be false. This true is already decided. They just decide that alpha 1 is false. Alpha 1, alpha 2 can be anything, doesn't matter, because alpha 1, alpha 2 here doesn't matter, because if left hand side is true, this whole expression is going to be true. We want this left hand side to be true. So we have done it by just making beta equal to true. Then to disprove this expression, we wanted right hand side to be false. So to make it right hand side false, one of them should be false. So we have taken the first bracket to be false. So to make first bracket false, the left hand side is already known to be true. The only option to make this bracket false is declare alpha 1 as false. So we have used alpha 1 as false. Then this bracket becomes false. 1 is false. Therefore, this whole conjunction is going to be false. So the right hand side is false and the left hand side is true. And what are you trying to say? Is true implies false, which is invalid. And therefore, whatever we are trying to do is invalid. So this expression is not a valid one. So done. This is not valid one. Okay, now let's get to the second problem. What is second problem? Let me note down here. Left hand side, it says there exists x, comma, beta implies alpha of x, which in turn implies beta implies for all x alpha of x. Done? Getting bored with color? Okay, let's change our color. So this is that means for all this is true. So for some values of x, this thing is true. So therefore, we get this in two brackets. So this is beta implies alpha 1, beta implies alpha 2. That is because of this comma I have written this way, and because there exist is there, therefore it is disjunction. So that's what happens on the left side. On the right side, what is it saying? It is saying this for all is there only attached to alpha x, not like this with a comma. Therefore, on the left hand side, it is only beta, whereas on the right hand side, you have alpha 1, alpha 2, alpha 1, alpha 2, and because it is for all, this is separated by conjunction. Same again, I don't want to prove this is true. Let me disprove this statement. So to disprove this statement, I want somehow to make this end false and make this end true. Done. So to make this end false, what is required? To make this end false, what is required? There is only one option. This should be true and this should be false. To make this whole thing false, only one option is left hand side should be true, right hand side should be false. And right hand side here is made up of two things, alpha 1, alpha 2 with conjunctions. Therefore, either alpha 1 can be false or alpha 2 can be false, or both alpha 1, alpha 2 can be false. Any one can be used to ensure that this right hand side is false. So some possibilities for this. Okay, coming to the left hand side, we want left hand side to be true. So for left hand side to be true, you may make sure that one of them is true, because there is disjunction here. One of the two brackets, make sure that it is true. So which one you want to make true? So let me say this is true. So let me say that the first bracket is true. So to make sure that first bracket is true, what would happen? The simplest way of making this inference true, so make the left hand side true, then left, make left hand side false, then irrespective of what is there on the right hand side, this whole inference will become, sorry, the inference will become true. So just making beta equal to false, this whole thing will become true. So what can be alpha? Alpha can be anything. So alpha can be false, alpha can be true, doesn't make any sense here. And since beta is false, this also guaranteed to be true, and true or true is guaranteed to be true. So just by making beta false, you can ensure that this whole left hand side is true. How about right hand side? What do you want right hand side? Right hand side to be false, and you have seen that it is true is left side, and for making this false, the left hand side be true. And for making this, you need a right hand side, this beta to be false. For this, you want a true. For this, you want a false. So something not matching. Here, for this to make false, you want beta to be true. For this, you make true. You want beta to be false. So there is some mismatch. Okay, let us stick to this. So confirm that to make this false, let me assume beta is true. So can we have beta true and this whole thing is still false? Keeping beta true, can we have this whole thing false? Yes, it is possible if beta is true. If we want it to be, if have equal to true, what we have alpha to be true, alpha 1 you make true. So alpha 1 is true, beta is true. So true infers true is true. So this you wanted false. So for that false, one of them should be false. But this has forced your alpha 1 to be true. So ensure that alpha 2 is false. By ensuring alpha 2 to be false, this becomes false. And making this true, this whole thing will become false. And because to make this false, we have assumed beta equal to true, and that true we have substituted here. This simple way of solving this did not help us. Therefore, let me take beta as true, which is required this side, and beta true, and this some value, and still this whole thing is true is possible only when alpha 1 is true. So that way I can make beta true, alpha 1 true. I can ensure this first bracket is true. And this is this whole thing becomes true just because this bracket is true. This bracket is true because beta is true, and alpha 1 is also true. Beta is true, alpha 1 is true. So beta is true, alpha 2 may be true or false, doesn't make any sense because this bracket has already become true, which makes this whole square bracket true. This side, beta is compulsorily true because you want the right side to be false. So this only option is true false option. If this is true, this is false, only then this operator will become false. So making this true is compulsory. Therefore, the simpler way of solving this was making this false. We didn't use, we just forced to take is true and get alpha 1 as true. So beta is true. We want this to be false. So for this to be false, anyway, alpha 1 is forced to be true. Then make sure that alpha 2 is false. Yes, I can ensure alpha 2 to be false. Yes, this combination is possible. Beta is true, alpha 1 is true, alpha 2 is false. With this is true, false and true and false is false. So true implies false is false. True implies true is true. True or anything is true. So left hand side is true. Right hand side is false. So left hand side is true. Right hand side is false. And hence the implies fails. Therefore, I can conclude that this also is not a right one. Okay, let us try to disprove the third one. What is the third one? For all x, alpha of x implies beta, which implies for all x, no, sorry, there exists. Is it right? Yeah, left hand side is there exists, right hand side is for all. If you look at it, there is comma in both the places. That means for this whole thing, this is applicable. For this whole thing, this is applicable, which means that on the left hand side, we have alpha 1 implies beta or alpha 2 implies beta. On the right hand side, it says alpha 1 implies beta and alpha 2 implies beta. Want to disprove this? So ensure that this whole thing is true and this whole thing is false. Done. So how do you make sure that the right hand side is false? So ensure that one of them is false because there is conjunction here. If one of the two brackets is false, that is done. So let me assume that this is false. So for making this false, what is required? For making this false, the left hand side should be true, right hand side should be false. So which says alpha 1 is true and beta is false. Only then this alpha 1 implies beta becomes false. Done. So this has become false. So for which we have assumed alpha 1 to be true and beta to be false. So let me apply that here. Alpha 1 is what? True. And beta is false. So true implies false is what? False. And you want this whole thing to be true. Therefore, you are forced to make the left hand side true. This right part of this of left hand side true because this part is false. And if you want the whole thing with the disjunction, at least this has to be true. For this to be true, so let me assume alpha 2 to be false. Done. So what is it happening? alpha 2 is false, and irrespective of beta, false implies false is true, so this is true. Alpha 1 is true, so true implies false is false. Why? Because we wanted this to be false, therefore we said alpha 1 should be true, beta should be false. So this has given false. So false being false, whole thing is false. So this thing is, we are trying to make the left hand side true. So while that alpha 1 is fixed to true, alpha 1 is true, beta is false. So true, false. What happens? This is false. And what about this? So can we make this true? Yes, we can make this true if alpha 2 is false. If alpha 2 is false, whatever be beta, this is going to be true. So if I use alpha 2 to be false, then this left hand side will be true, and alpha 2 to be false, this is true, but this is false. So false and true is going to be false. Therefore, left hand side is true, right hand side is false. Therefore, this also doesn't hold. Third one also is invalid. Now looking for the fourth one. For x, x implies beta. Fourth one, it says for all x, alpha of x implies beta, which implies for all x, comma, what? Alpha of x implies beta. Okay, this both are the for all. Only thing is there is no comma here. That means this are connected. There is a comma here. That means this is connected. So this are alpha 2 implies, which in turn implies this applies both. So it says alpha 1 implies beta and alpha 2 implies beta. What do you want? Left hand side to be true, right hand side to be false. That's the easiest way of disproving that this condition is true. So just to make sure that left side is true, right side is false, see how to make the right hand side false. There is a conjunction here. Therefore, one of the brackets, if you make false, then the whole thing will be false. So how do you make this false? So to make this false, one option is only one option is alpha 1 should be true and beta should be false. All other cases, it is going to be true. So if alpha 1 is true, beta is false, only then this is false. So if one is false, that is sufficient. No need to make other one also false because there is conjunction here. Okay, coming to the left hand side, you want to make sure that this is true. So to make sure that this is true, what is the simplest way is to make sure that this is false. If you make this false, false implies anything is always true. So the simplest way is side false. What is left hand side? Left hand side is alpha 1 and alpha 2. So to make sure that these two are, this whole thing is false. Alpha 1 is already taken to be true. Therefore, alpha 1 cannot be true. But you want to make sure that this is false. So to make this false, alpha 2 should be, alpha 2 can be anything. Alpha 1 is already true. Therefore, alpha 2 is forced to be false. If alpha 2 is false, then this is going to be true. and this is going to be false because alpha 1 is true, beta is false. So one false and anything is going to be false, and this is false. So false implied anything is going to be true. So this condition holds. Therefore, this one is also invalid. So this is true, this is false. So there is some value of alpha 1, alpha 2, and beta such that this left hand side can be proved to be true, right hand side can be proved to be false. So for this combination, this doesn't hold. Therefore, we can say that this is also not a valid one. Okay, this way. So what we did. So this is what logically at a human knowledge level, if you're arguing, then all these arguments were done. But that's not possible when it comes to machine level. Therefore, we have some rules called inference rules. If these inference rules are applied, then whatever we have done earlier can be taught machine to repeat. Okay, one is universal generalization. So here, if you know that px is true, so for what value of x is given? No, nothing is mentioned. It's just mentioned that p of x is true. So it means it is true always. So whatever be the value of x, it is always true. So if it is not clearly mentioned that it is true for only one value or two value, then yes, we can generalize that it is true for all values. Second one is universal instantiation, the opposite of this. The opposite of this is universal instantiation, wherein you know that this is true for all of x. You know that it is true for all values of x. Then we can conclude that it will be true for some c. In place of x, you just say for some c. It's like you are saying all dogs are mammals. Yes, it is true. If p is property called mammal and x is used for dog, then you can clearly say that all dogs are mammals. And you're talking about one particular dog, Tommy. Yes. So Tommy is a dog, therefore Tommy is a mammal. So you're talking about particular instance. If it is true for uh, general, then it is true for a particular instance. So this is called universal instantiation. And the same way, you have essential generalization. This applies to, we know that some C is true. For some C, P is true. That means some for some puppy, the that is a mammal. So you know that this is talking about mammal, and C is a dog, a particular dog. C is a particular dog, and if you are saying that this particular dog, this C is a dog, and that dog is a mammal, then you can generalize that there are some x such that p of x is true. There are some values of x such that P of x is true. Now I cannot say for all. I cannot say for all because in some cases we need to, when you are not sure that it is true for all, then you have to say that for some it is true, because you know that at least one is true. P of, for C it is true, you know that. Then you can say there exists some x such that P of x is true. That means in, now if I substitute C in place of x, then I am sure that it is true. So if one is true, then this whole thing is true. Same way, the opposite of this is essential instantiation, wherein it says if there exists some x such that P of x is true, then some particular d, it is also true. Now only while using this thing, so just ensure that d is a new variable or constant. Don't repeat it because it is saying there exists some dog. So somewhere in the back you have used there exists some dog, and for that you have used P of d. Now in later stages when you are working on some proof, you come across with similar formula again. So now this formula is talking about there exists some cat. Then if you say P of d again, then sometime you say d as dogs, now you are saying d as cat, then there is confusion, there will be conflict. Therefore make sure that such conflicts never arise. Then whenever you are writing this part, this d has to be a new one. If d is not used earlier anywhere, then use it. Just because I am talking about, now you may ask, this is c, this is c. Yeah, this is for all. This is for all you are saying. Therefore when for one c is there, then for other time if it is same c, then also it will be true. But here it says for some. Then when you say for some, then the same thing for some other formula it may not fit. Therefore make sure to use a new symbol here, not to repeat the same symbol. That's one thing you need to remember while working on this. So this four rules of inference help us to solve all this. We can use these four rules of inference and solve this. We can write an algorithm so that these rules can be applied to these things. So it is saying for all alpha x, yeah, for all alpha, for all x alpha x. What should I write here? I should write something. Then there exists. What should I write? I should write something. And if it is beta only, then if it is beta only, then I can replace it with for all beta. If beta is a function of x, but here it is not looking like beta as function of x, therefore it appears like something this, then you can make use of this formula there, and so on. Okay, we are running out of time. We have many other things to do. So when we have some more free time, let us get into how to solve this through a machine using these rules. So currently it's not required because we are in fag end of our semester. So before your mid exam, we need to complete our 2.5 units. So I'm just making it fast. The next thing is something called chain rule, which is a simpler way of solving these things. We use a chain rule. There are many, what do you say, premises given, and these premises can be used to continue working with. And there are two ways of working. So, in solving or in proving, or better way is called reasoning. So, chain rule for reasoning. So, you are using the whatever statements are given, you are using those statements and trying to imply. So, let me start with an example to talk about. So, when we go to a doctor, our doctor will ask for some symptom. What has happened to you? So, you will tell some symptom, and from that symptom, he will conclude something. From that symptom, he will conclude something, but still, he is not very sure what to how to medicate. Therefore, he may ask some more details. Then you may give one more symptom, and this symptom and the past conclusion together, he may get another conclusion. And if this is also not sufficient, then he may ask you to give some more details about the problem. So, looking at the new symptom and this conclusion, if he is now clear enough what has happened, then he will decide what is the problem, and then he will find the disease and then prescribe what to do. Now, what is happening is you are giving him three things as input: S1 symptom, S2 symptom, S3 symptom, and on the way, he is using some knowledge he has. So, one knowledge he has is, if symptom 1 is there, then he can conclude with conclusion 1. And if symptom 1 and conclusion 1 are given together, then he can conclude this. And if symptom 2 and conclusion 2 is given, then he can decide what is the disease is. So, what are we telling? Is it confusing? Yeah, definitely. What did we say? From symptom 1, he concluded conclusion 1. From symptom 1 and conclusion 1 together, he concluded. So, I can say that symptom 1 and conclusion 1 will lead him to conclusion 2. So, let me say that this is an AND operation. Both together will get you conclusion 2. And then we said that symptom 3 and conclusion 2 together will get you to identify disease. So, this is it. So, this way I can represent graphically, but in reality, I am trying to say S1 implies C1, S1 and C1 implies C2, S2 and C2 implies D. Okay, what has happened? You start from inputs, then you have some knowledge. We have some knowledge which doctor has gained while he is studying his course, medicine, and any other upper higher end courses. So he has built up knowledge. So all this thing is in his brain. So let us call that the knowledge bank. And this all we are feeding as a input. So let me call it data. And this whole thing is stored somewhere in a place called data bank. And from that, you are going to come to a decision. So this is what you say, because patient said this, I could understand this, and because I understood this and patient said yes to, I could understand this, and because patient said S3 also and C2 I could understand, then I can decide that what is the disease. And looking at the disease, I can prescribe. That's what he is reasoning. So one way of reasoning is what we call forward reasoning, which is from the source to destination, and the other one is the backward reasoning, which is from destination to source. Okay, how do you solve this? Okay, let's take a simple example. Yes, without example, we can solve. So the data bank consists of two things which we know A and B are true. And then we have knowledge bank, where first one it says A and C implies F. Second one says A and E implies G. Third one says B implies E. And fourth one says G implies D. So that is what we call knowledge bank. What do you want to decide? You want to decide is A and B implies D. So that means this is our source, this is our destination. So this is the source. We have to start from here. So we are given with A and B. So we can build. So the best way of solving this would be tree building. So if it is a forward, then it is bottom up approach. And if it is backward, it is top down. Okay, what do you mean by bottom up, top down? So you start from source, go to the destination. So we build a tree. Tree means you have one decision and you have many sources. You have one decision and you will have many sources. Therefore, when you try to present it as a tree, then on the top there should be a single node, and as you go down, the number of nodes keep increasing. That's how our tree structure looks like. Done? Okay, so that means on the top we have decision, on the bottom we have the source. Okay, let's start working on this. What is it trying to say? So let me start with a forward journey. It's called forward chaining or forward reasoning. When you are saying forward chaining, so I have to start with the source. Source given that A and B are true. So A is true, B is true. Okay, now from this, what all you can do? So if you want to use this, you need to know what is C. C is unknown. If you want to use second condition, you need E. E is also unknown. If you want to use third condition, you just need B. Yes, if you say B is true, then you can claim that E is true. So let me claim that since B is true, E is true. So this let me write this way. So since B is true, E is true. Done. Then I know E. First one I cannot use because C is unknown. Oh, second one is now available. A, E both are available. Therefore, I can now go for A and E. So take A, take E, and get what? What do you get from A and E? You get G. How? It said A is true and E is true implies G is true. Because B is true, E is true, A is true. So A is true, E is true, both are true. Therefore, A and E is true, and hence G is true. So we have reached till here. Now, what is required? You want to prove that D is true. And where is D? Oh, D is in the fourth expression. And for D, so luckily it is on the right hand side, which we want to conclude. So D is on the right hand side as it is. On left hand side, it is G. Do we have G? Yes, of course, we have G. So therefore, I can say that D is true. That is true. If G is true, D is true. Where did we start? We started from A is true, B is true. Okay, then what happened? Because B is true, E became true. So this was our first step. This was our second step. Or you can say both are step one given. Then because of this, this is second step. And 1 and 2 together, this one is made third one. Now I'm talking in time series. This is nothing to do with these numbers. These numbers, you know very well what this is. This is B implies E is the third one. A and E implies G is the second one. So don't get confused with these red numbers. These are time steps. I can call them time steps. Done. And finally, this is the fourth step because G is true. Therefore, D will be true. That's a fourth step. So we started with A as true, B as true. So A and B both are true, and which concluded that D is true. Done. So if this is going to imply something, then you get a correct answer. So you get this thing to be true. If there is inconsistency here, then you won't get this graph. You don't get this tree, and hence you can simply say that this is not a valid decision. Okay, can we say A and B implies F? Okay, check what would happen if I try to say A and B implies F. Okay, I start with A, I start with B, and B says it is E, and A and E says it is G, and G says it is D. Now, how to go to F? To go to F, I need C, and in my whole thing, nowhere I could see C. Therefore, I cannot get to go to F. I need a C, which is not available. Therefore, I can claim that with available information, this cannot be proved. Now, how can I prove this? Only one option. Then let us decide that C is already known to be true, or add one more inference here so that C comes on the right hand side. So that using through that you can get C true and then come to F to be true. As on now, without this C or any other thing, like a fifth one saying A, what is that? G or D or G implies C, because D is true, G is true, C will become true. So D or G, either of these two, will imply C to be true, and therefore this will also be true. Yes, you can prove if it is there here, or if you have started with another term here, which is C, which you are well known that it is true. So this is how a forward chaining is done. The same thing you can work with backward chaining. And for backward chaining, you need to work from the top. What top says? A and B implies D. So that means you need D to be true. For D to be true, A should be true, B should be true. Done? Okay. So we want D to be true. So where is D? D you can find in the fourth position, and fourth position says D can be true only when G is true. D can be true only when G is true. So when do you think G is true? Look for G on the right hand side. G will be true only when A and E are true. G is true only when A and E are true. So when do you think E is true? E is true when B is true. E is true when B is true. So we have started from the right hand side. We have started from the right hand side. D is true. So for D to be true, we used the fourth expression. For D to be true, G has to be true. For G to be true, we use the second one. A and E should be true. So A and E should be true. So let me put and operations here. So this special type of graph which are called and or graph. Somewhere back we had dealt with this and or graph. Wherever it's and, so we use a what is it, curve there to imply that these two should be ANDed. They are not OR. So if there is no curve here, it means it is OR. Done. So we wanted D to be proved. So we started from D and then started applying rule by rule, and then went down, 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 and finally we reached A and B, which are supposed to be the left hand side. And D will be true only when A is true and B is true, because there is and here. So A should be true and E should be true. For E should be true, B should be true. So in indirectly it is equivalent to saying A and B both should be true, which means this is proved. So this way you come down. That is top-down approach is the backward chaining or backward reasoning. So that's forward chaining, backward chaining, or forward reasoning, backward reasoning. So some uh, normal, we know some data, some information is available, some knowledge bank is available, and using information and knowledge bank, we need to take some decision. So for doing that, chain rule is applied from 1 to 1, 1 to 1, 1 to 1. We keep applying chain. So there is, you can find a chain like thing. We started from bottom, using this chain we moved to the top. or we started from the top using a chain, we came down to the bottom. So these are chaining or forward approach, backward approach, and this is a, um way of reasoning. This whole thing we call reasoning, and using these simple rules, using these simple rules, we can write algorithms either using forward chaining or backward chaining, so that you are given with data and given with knowledge bank, you can make your algorithm to prove or disprove whatever the decision is. So if it allows, then it is proved. If somewhere stuck up, yes, naturally it is disproved. So this is how you start reasoning. Done. So as of now, that's it. I think another 1 or 2 periods we require for completing, because next one is talking about probability based theorem, and it's a very important one for our future. So I expect none of you to miss the next session. So next session details will be uh, given to you shortly. So make sure to attend. Okay. So time to say bye. See you soon. Till then, take care. Bye.